We will learn how to design state machines. We have been discussing sequential circuits, how to design sequential circuits using VHDL. And in the physical classes, we introduced the process statement, the process construct, and everything that is written after process will be executed sequentially, will be synthesized sequentially. We had done few examples and we had introduced an if statement, which is the most frequently used statement to design sequential circuits in VHDL. But there's a one powerful statement in VHDL that's often used, that actually is used to, code their finite state machines. FSM is a universal approach that is used to design any kind of a sequential circuit. Right? Now, based on FSM, we actually have a five-step methodology that I have listed here. When we design sequential circuits using pen and paper method, we start by capturing the finite state machine that describes the behavior. In fact, here you can capture FSM as a Moore machine, or you may capture it as a Mealy machine. Right? And then the second step is you create the standard architecture. The standard architecture of a sequential circuit is that it has a combinational logic, a combinational block. Then in the feedback path, it has a state resistor. And it is the current input and the outputs from this state register, which basically are your previous outputs that are being stored, that will give you your current output. Fine. So this is the standard architecture of every sequential circuit. So we create a standard architecture based on the FSM description. Then we encode the states, we create the state table, and finally we implement this combinational logic, and that gives us the overall implementation of your desired sequential circuit. This is a very universal method, must have studied in the digital electronics or in the computer architecture. Fine. Now for VHDL, we only need the first step. We only need to know what the finite state machine description of my circuit is. And if you know the FSM description, then you can actually use a very powerful statement that is in the VHDL, the case statement. Right? And actually, our topic of discussion is this very statement, how we can use the case statement to design a sequential circuit given a particular finite state machine. So first of all, the general syntax, it starts with the keyword case, then there is some sort of an identifier, then there's a keyword is. Then this identifier can take multiple values, and for every value of this identifier, there will be an assignment. And then once you are done with all the values of this identifier, you end your case statement. Right? So the syntax is simple. It's quite literal. You have an identifier for which multiple cases can exist, and for every case, you will have a particular assignment. Right? So let's quickly take an example here of a typical sequential circuit, and let's see how we actually employ this case statement. So here I have a counter. We had actually designed this counter using the if statement, but this time around we will design it using the case statement. So it's a counter that counts from 0 to 9 and then resets back to 0. So it will have 10 states. So this is the finite state machine that I have already drawn here. It has 10 states starting from state 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, back to 0. Then in every state, there is some output. For example, if my circuit is in state 0, the output will be 0 in binary. I have used 4-bit binary to cover all the outputs. In state 1, it will have the value 0, 0, 0, 1. Similarly, in 2, 0, 0, 1, 0. 3, 0, 0, 1, 1. For 4, it will be 0, 1, 0, 0, and so on. Right? And in the finite state machine, we also have to show the transition. Now, this is a very simple case. Here, I am assuming that every time a clock pulse happens, there is a transition. So we don't show the clock in an FSM, but this basically happens when there is a positive transition of clock. Similarly, this transition happens at the positive edge of the clock. and so on. Then again, as a convention, we have to choose an initial state that we typically show using this arrow. So 0 is my initial state. So this is the FSM description of a 0 to 9 counter that resets itself when the count reaches to 9. Right? Now let's try to code this. We have the finite state machine. Let's try to code this using the case statement. Now the first part, library declaration, it is the same. You will have a library IEEE and then you will define some packages. Then the entity part again is the same. I have named it counter. So the entity name is counter. Then I have defined clock as the input port and I have defined output as an output port as std logic vector 3 down to 0. Then we start the architecture behavior. Yeah, since we are using FSM, so to add a literal meaning to it, we have the FSM. आप कुछ भी लिख सकते हैं. Then the entity name, then case. Now there will be the difference, right? So if you remember when we had discussed it in the earlier part, the data types, we had the predefined data types, and PHDF also gives you the flexibility to define your own data types, what you call the user defined data types. And the way we define them is using the statement type. So I will define a user defined data type here immediately after architecture, the keyword type. And I will call this type, let's say state, then is. And as many states as I have here, I have 10. So I will define them as the different values that this new type can take. So type state is, then I will list all these states 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I have defined a new type by the name state, and this new type, this state type, can take any of these 10 explicit values. Right? Keep in mind that this is my FSM and I'm trying to code it. Then I will define a signal. In fact, I will define two signals. One I will call previous state, PR underscore state, and the other one I will call next state, NX underscore state. And I will define these two signals of this user defined type state. Right? Again, I will repeat, I have defined a user defined type state that has all the state values. जितनी भी आपकी states है FSM में, those are explicitly mentioned as the values that this user defined data type can take. Then I will define two signals, signal previous state and next state of this user defined type. Fine. So this is the new thing that I have done. Then there is begin. So it will be there. Now this is a sequential circuit. So if you have to code it, you'll have to use a process. So with use a process, again, this is a given. And this process will have a sensitivity list as a clock signal. Fine. Then as usual, we'll use the if clause. So if clock event and clock is equivalent to 1, then there will be a transition in which previous state will be equivalent to next state. Then I will end the if statement and I will end the process. So this small process that I have initiated here, it basically defines the transition that every time a clock event happens, I will be moving from previous state to next state and so on. Fine. Again, this is trivial. We have done this. Next, I will initiate another process, and this is the process wherein I will be using the case statement. another process, and in this process I will be using previous state, which is a signal of the type state, as a sensitivity list. Then it will have its own begin, and now I will use the case statement. So case, the keyword, then I will choose this previous state as my identifier, then is. Then for every value that this previous state can take, and it can take 10 values, I will have to explicitly define, say for example, when 0, when the value of this identifier is 0, then in that case, I have to define two things. First, what my output is going to be. So output will be 0, 0, 0. And another thing that I have to define is from this state, what will be my next state? So next state is 1. Fine. Then when 1, this is the second value that this identifier can take. Again, I will define two things, that in this state, what my output is, and from this state, what's my next state? That will be 2. Right? Then the third value that this identifier can take is 2. Again, when I'm in this state, state 2, I have to define what my output is. And from this state, what will be in my next state? 3. Likewise, if you continue, then the next value that this identifier can take is 3. And when you are in this state, your output will be 0, 0, 1, 1. And from this state, the next state is 4. Likewise, it will continue. And ultimately, your last state or your last value for the identifier will be 9. And again, in this state, I will have to define what my output is and what my next state is. So after 9, I will go back to 0. I have covered all the 10 states. Then I will end my case statement and the process statement. And then end the architecture like this. So this is how we code a finite state machine, right? So few things that are important here. First, you have to define a new type, and that type should have values, which is actually the number of states that you have in your finite state machine in this particular statement. Then we define two statements because we have, as far as states are concerned, we have previous state and next state. So I will define them as the two signals of this type. Then you will have the initial process that will define the transition from one state to the next state, for which I have this small process, the first one. Like in this case, it happens with every clock event, which is implied. This basically defines your condition for an implied transition. So we'll take some more examples wherein we will add additional signal signal that define the transition. But when an FSM is constructed, one thing is implied, that this transition will require a positive edge of the clock. This is an implied thing. You may have some additional conditions that you'll have to take care of, but one thing is always implied, that transition will happen at the positive edge of the clock. Fine. So therefore, that implied thing, we always have this small process that start with. Then the next process will define two things. First, it will define what is the output in a particular state, and second thing, it will define from this state, what will be your next state? So for this case, we have to go case by case. So we use a case statement over this signal. We take this signal as an identifier, and for this identifier, we define whatever the number of cases is. Like in this current example, we had 10 cases corresponding to 10 states. So for every state, I define my output, I define my next state. Then I move the next state, output, next state, and so on. So when you code it, when you write in this, your synthesizer will understand this machine and it will come up with a counter, the decade counter, the counter 0 to 9. Fine. So this is the finite state machine approach using the case statement. As far as test bench goes, it is the same that you used. Again, there will be a process, so we have done that. So quickly take another example. This time around, I have an up counter, and the design statement is that we have to design an up counter that counts from 0 to 7. Up counter is that counts in an increasing order. The one we defined is also an up counter, 0 to 9. But there is a twist here that the transition from one state, this is the thing I was talking about, from one state to the next state is governed by an external input P. So there are two things. Clock will still be there. When you move from one state to the next state, clock is implied that it happens at the positive edge of the clock. Now, simultaneously, you have also to take care about of an external input B, and when B is equal to 1 and there is a positive clock edge, then only you can move from one state to next state. If B is 0, even if a positive edge of clock comes, you cannot move from one state to the next state. You are stuck in the same state. So this is the finite state machine. There are eight states: 0, 1, 2, 3, 4, 5, 6, 7. In every state, I have defined the output. And these green transitions, these are basically the clock transitions. Now, this is an incomplete FSM because I have to yet include B in this. Fine. So for that, to include B, see what happens. We start with an initial state 0. If B has a value 0, which we normally show with B complement, then I will stay in the same state. Right? And this transition, apart from a positive edge of the clock, I will also have to ensure that B is high. Okay? Similarly, when I'm state 1, if B is 0, which we show by B complement, you'll stay in the same state. If B is 1 and there is a positive edge of the clock, you will move to state 2. Similarly, in state 2, you will stay in the same state. If B is 0, you will move the next state if B is 1. Then in state 3, same thing. Fine. B complement, B. And in the final state, again, you will stay in the same state. If B is 0, you will move to the next state if B is 1. Now, this is the complete finite state machine. Fine. And this is the only thing we need for VHDL. Fine. So let's code this FSM. Again, I will have some library declarations, library IEEE, then you will define your entity. I've called it up counter. I have clock, which is implied, and this time around I have an additional input B. Both will be in std logic. Then I have defined the output as count as std logic vector 2 down to 0. I need only 3 bits to represent numbers from 0 to 7. Then there is an architecture, and the first thing we will define the state. We'll define type. Again, let's call it state. And the values that this user defined, that this state can take, are again the number of states that you have. So this time around we have 8, 0, 1, 2, 3, 4, 5, 6, and 7. So explicitly I have to mention the values that this user defined type can take, which are actually the number of states. And as usual, I will define two signals. Signal previous state next state, and I will define these two signals of the type state. Fine. Then we'll have a begin. Again, this is a sequential statement, so I'll have to use a process. So the first process that I'll be using will have clock as a sensitivity list, and this basically defines the implied transition. If clock event and clock is equivalent to 1, then previous state next. But don't be confused here, huh? Because only the clock transition will not define the transition, because we also have an external input to take care of. That I will define in the next process. I have told you that if there are multiple processes within the same architecture, they run concurrently. So it means, like in this case, this process, whatever is inside this, will run sequentially. This process, whatever inside this, will run sequentially. But overall, this process and this process, they will run simultaneously. Right? So keep that in mind. So we actually exploit that nature here. In the first process, just to be consistent, just to have a standard structure of code, we define the first process for the clock itself. Right? But this will not define the transition, because in this case we have an external input B that I will define in the second process. So I have completed the first process for the clock. Second process, I will initiate. I will have previous state as my sensitivity list, and I will also have the second input B as part of the sensitivity list. Fine. Then it will have its own begin, and after begin we will use the case statement. Case, we will choose previous state as our identifier. Then for this identifier, you can have multiple values. So when this identifier has a value 0, again we'll have to define two things. What is the output? So we had defined, I think, count. So when 0, then count will have a value of 0 in binary. Fine. And the second thing that we have to define is the transition. Now, in the previous case, the transition was defined only by the clock, and clock was already defined in the first process. So in that case, we simply wrote next state is 1, right? But here we also have to consider the input B. So this will be modified here. So I will use a small if clause here, that if B is equivalent to 1, then next state is equivalent to 1. Fine. And if this is not the case, then we'll have a small else clause. Next state will stay at 0. Right? Then we will end if, and we will proceed for the second value of this identifier. So when 1, then count is equivalent to 0, 0, 1. And again, this if statement, because we have to check it for every transition. If B is equivalent to 1, then next state is equivalent to 2, else next state will stay at 1, and if, right? Then the next value of the identifier, next case, you can say when 2. Again, first we'll define what is the output in this state, then the transition. So if B is equivalent to 1, then next state is equal to 3, else next state will state to end if, and so on. And the last case will be when 7, wherein count will be 1 1 1, then if b is equal to 1, then next state 0, else will stay in the same state. Then we will end if, right? So all the 8 states have been defined, what the output is, and how you can move. So you can actually end the case statement. Fine. Then end this process. Then end your main architecture. Right? So when this code will execute this process and this process, they will execute concurrently. So this process will check for the clock, and this small if statement will check for the condition on the input B. Right? So this is how you code up counters. I'll end this video. I will upload a few more videos wherein I will take some more examples. We'll define their finite state machines, and then we'll see how we can code them using the case statement. But this is pretty much the standard. There are multiple ways of using the case statement, but the one that I've shown here is simple, and it kind of is a kind of a general kind of a code. The only change you have to make is that within a particular state, what your output is and how you transit from current state to next state. If it's only clock, like in the first example, then you directly show the transition because clock is taken care of in the first process statement. If there is some external input, then obviously you will have to define the condition on that input within every clause of the case statement. So stop here.